Okay, so here's that same example RL circuit that we've been looking throughout the lecture, but now I drew it in LT-Spice. I'm going to set the source voltage here equal to, we're going to do an AC analysis, so I can get the transfer function, or the magnitude and phase response. I set that equal to 1, because really what I'm interested in is the ratio of the output to input. But if I set the input to 1, the ratio of the output to input will just be equal to the output. So I can get the magnitude response just by setting my source value equal to 1 at an angle of 0, and then just plot the output voltage, which is the voltage across the resistor. The other thing now is, instead of doing just a list at a single frequency, I'm going to plot frequencies between 10 hertz and actually 100,000 hertz in this case. So plot the so what LT-Spice is doing at each of these frequencies, and I'm choosing to do 40 points per decade. So it'll evaluate the frequency response at 40 different frequencies between 10 and 100, for example, and then another 40 frequencies between 100 and 1,000. And at each one of these frequencies, it's changing the frequency, computing a new impedance for the inductor, a new j omega L value, and then doing the circuit analysis. So I'll see the output voltage actually as a function of frequency. So let me run the simulation. So it looks like this. So let me expand this. By default, LT-Spice produces this magnitude response on a dB scale with a semi-log x-axis, just like what we're using for our Bode plots. Now the solid line here is the magnitude response, and that's what we're concentrating on. And so the solid line corresponds with these values over here on the left. The dashed line is actually the phase response. We see the phase response here goes from 0 degrees at low frequencies to a negative 90 degrees actually at high frequencies. I can right click on there and say don't show the phase if I don't want to see the phase. Now again, a couple different things that we've looked at this actually on a linear scale. You can choose to plot this on a linear scale. This looks a little more like what we've seen in the past. Notice that the x-axis is still logarithmic here. Now if I change it to a linear scale, it's going to look really strange, because I'm going from what was it, 10 to 100,000, so over that logarithmic scale. But now things are really compressed here. I'd want to go back and change the way I at the frequencies I choose to do the analysis at. So let me go back to the logarithmic scale here. Let me go back to the dB scale here. Okay. And then, and this is a little different than what our Bode technique looked like, but it's pretty similar. Let me actually show you how similar it is by actually copying this over into Paint. So here's the LT-Spice copied over into Paint. Now actually let me go back and get my pencil tool, and I did red before. If you remember, what I had was 0 dB up to my passband frequency. In this case, the omega p value was 1,000, and then for above 1,000, remember I went down at above a decade above 1,000. Which is 10 kilohertz, I'm down at this minus 20 dB. Notice that's what this is. This was minus 20 dB. A decade above that, I'm at minus 40 dB. So again, this line would continue forever, right there. Notice how LT-Spice actually is evaluating the frequency response at each of those different frequencies. This Bode technique is just a quick graphical approximation to the actual frequency response of this circuit. And notice it is pretty good. I mentioned it's off by 3 dB here. This line is negative 4 dB. So the actual response is 3 dB different at the knee, but for frequencies below that omega C value, that critical frequency or corner frequency, or well above it, the Bodhi technique gives me a very good approximation to the actual frequency response. With a little practice, you can get to the point where you draw these Bodhi plots. You can draw these Bodhi plots really quickly, and so you can get a very good, back of the envelope approximation to what the magnitude response of this thing is really is. Now, it is true that we've got tools like LT-Spice that will quickly draw the exact magnitude response for us, plot that. You can also do this in Octave or MATLAB really easily. So why do we need to resort back to this hand-drawn approximation method that engineers have used for decades in the past prior to having our modern software tools? Well, part of the reason is that filters are specified still in terms of kind of their Bodhi transfer function. It may have a 20 dB per decade roll off above 2 kilohertz. And in the design procedure, we have to translate those Bodhi specifications into an actual circuit. In order to do that design, you have to have a good understanding of the analysis and how to generate these Bodhi plots. So, in the design, you'd typically be given maybe this quick hand-drawn approximation of the desired filter response, and then have to actually translate this back into a frequency response, and then from the frequency response generate an actual circuit. Okay, that is it for today. I may be recording lectures and posting them all this week. The forecast looks pretty bad this week. If you have any problems or concerns, about any of the lectures, please email me. I'd be happy to try to answer questions by email. Be happy to set up a virtual Zoom meeting with you. While we are closed due to snow, we won't be doing labs. Okay, I'll continue to actually record and post the lectures, but I'll give you a little bit of a break in that we won't be doing any lab exercises or lab experiments when we're closed due to snow.